give the wrong impression. So what I found helpful is to start right from scratch. Actually, that's what I find helpful. But yeah, I mean, of course, it's just it's this thing. Anyway, I'm going to try to emphasize that today. That to just look at it from a very yeah, without any preconceived notions about anything at all. So yeah, but if you want something midway, you see the thing with Haskell is that it takes a while before somebody gets to a stage where you can do things which are non-trivial. But if you want something which is not which which is a little gentler, then ML, standard ML, and OCaml especially, that's the dialect which is now very popular, and that is the one which is perhaps a little better in this regard. So uh, the complaint about Haskell usually is that there is too much to at one shot to get used to before you start doing something which is non-trivial. So, but it's before you start doing anything, actually, even something trivial. But it nevertheless is an interesting language. I mean, you see, like they say, if you want to learn small talk, if you want to learn object-oriented programming, I've never cared much for it though. One should actually program in small talk, because that essentially gives you a feel for exactly what object-oriented programming is about. And the same thing with Haskell. If you want to learn functional programming, Haskell will pretty much not allow you to do anything other than functional programming. And at the end of the day, after grappling with things, you'll get used to it. You'll get used to the style of functional programming, and then it'll feel natural compared with what you felt before.
Right. Also, what about Scala? I mean, I've also looked at Scala.
Yeah, so Scala Scala's borrowed a lot from Haskell, and it is influenced a lot, not just Haskell, but even ML and all of that. Scala, I believe, is a language which has very nicely. This is what I've heard. I've not really gone into Scala much. You see, Scala had a few properties which I was not very, which was a bit of a game changer for me. One is, I think it has probably the tail call optimization, and the other thing is, the syntax also is a bit uglier than one is used to. And either way, I mean, for me, it was just like what I needed to do. So I didn't have to reach for Scala beyond Haskell anyway. But Scala also has that. But the only problem with Scala is it'll allow you to do some of these things. But I think, again, the thing is that since you can do other things also, it's probably easy for people to slip into a non-functional style and not learn much of it. That's the thing. I mean, if you want to really learn functional programming, then I think these ML family of languages do a good job. And also in Lisp, I think the emphasis, the culture tends to be quite, functional. But I think between them also, I mean, if you really want to just learn functional programming, then of course Haskell is the bestest thing, because it essentially you can think of it as an experiment which is stretching functional programming to its limits. And they have a slogan: avoid success at all costs. What they mean by that is they don't want to get too weighed down by backward compatibility that they cannot experiment. And so they keep experimenting with the language. They keep introducing various features and so on, and exploring this whole functional programming paradigm. And so that is the thing. So Haskell, on the one hand, if you really want to learn it properly, then Haskell. Anything else is like, it'll give you the opportunity. You can try it if you want to, but you'll have to yourself be very careful about not using, not falling into other things. Of course, there's nothing wrong with the others. It's just that if you want to, you'll probably not learn some of the useful features of functional programming if one thinks that what one already knows is an easy way out, because you don't really appreciate the importance of this kind of concept and so on. So, but again, I have not programmed.
I think we can start.
Yeah, sure. We can begin now.
Yeah. So,
all right.
Okay.
Yeah.
Yeah. Okay. So the recording's on. So yeah. So welcome everyone. We'll begin our talk on functional programming, Introduction to Functional Programming by Shane DeMello. Sir has taught us. Well, we got to know Sir through a course which he took, which was Theory of Computation, which was frankly one of the best courses I have ever attended. So we asked him. I mean, he's not someone who researches in programming or something as such. His core this thing is in math, but he is pretty interested in functional programming as under the thing of all of programming. And yeah, so we'll begin. Turing Club would also like to thank the Dean Acad of Isa Mohali for providing the Zoom account. Yeah, thank you.
Okay. Thank you, Dhruv. Thanks a lot. Yes, so yeah, I'll start the main part of the talk soon. But before that, I just want to give a few disclaimers because I think one attends a talk with a certain thing in mind, and over here my goals are slightly different from what a standard one would be. So first and foremost, I will be probably be bombarding you with a lot of with a lot of different examples and codes and so on. I'm not doing it with the intention that you should actually pick up those details and that you should understand them completely. Because if I set, teaching functional programming or teaching Haskell as a goal, that would certainly not, the 1 hour is certainly not at all sufficient for that. So instead, my goal is a lot more modest than that. What I want to do is I will pick up a few ideas that I have personally found useful. And I just want to share those with you. And as a result, sometimes, in fact, quite often, I'll show you snippets of code which illustrate those ideas. Do not worry if you are not following everything in that. Okay, it's just pick up on maybe it'll suffice if you just sort of understand that what the main idea is, or just visually, this is what it looks like. Just note that it's short, note that it's clean, and I'll keep telling you what was different and so on. Also, I'll be speaking a lot more than I'll be showing you on the screen, because on the screen I'll just mainly show you code. But you need to focus on what I'm actually saying to understand the context and so on. I don't want to have too much on the screen in one shot. So and the other thing that I want to say is that functional programming for me is partly, of course, I like it, and the second thing is it's just something that I use when I need to program something. I have used it in my work, but not really in work that I collaborate with somebody and so on. So I had to use functional programming at that point of time. And I also use it when I want to maybe get something done and I wish there was a tool for that particular purpose, and it's not available, then I reach for it again. And so I find that it's quite. I find it elegant, and I find it easy to kind of think in terms of Haskell once you kind of pick it up. So that's why I'm focusing on it. Okay, I'm not making any claims about being an expert on it. There might be a lot of gaps. And in functional programming in general, there might be a lot of gaps in my understanding of it. Worse still, apart from not knowing a number of things, I don't even know what I don't know. Okay, so it's a bit, so all I'm saying is take this talk only in the spirit that you're trying to just see what is interesting. And if you do find it interesting, then you'll know what to look for and hopefully where when I give you the references. And also when you're reading, when you finally, if you finally decide to learn functional programming or Haskell for that matter, then hopefully, you know, some of the comments that I have made will help you to imbibe that better, and that you will actually, you know, understand things, and you'll also have another context, basically. All right. Think of it as also some of the things that I'm telling you are, you know, what come in the category of what I wish I knew when I was learning Haskell. In fact, there's a blog of that particular name written by some. I forgot to actually include it in the list of references here, but if someone could remind me at the end of the talk, I'll find out the exact name and the author's name. But that blog does a very good job at. I'm not trying to replicate that at all. I'm giving you my own perspectives and so on. But anyway, that blog is also an interesting reference, which I just remembered. So. Anyway, now let me begin with the main part of the talk. You know, when you think about computer languages, you know, there's, I mean, some of you may have heard of this term called, many of you might have heard of it, of this term called Turing complete. But even if you have not heard of it, it is enough to know that if a language is Turing complete, then anything that you can do in that particular language, you can do in any other language that is Turing complete. All right. So any kind of problem, any computational problem that you can write a program for in one language, in one Turing complete language, you can also do it in another one. So in a certain sense, what they can do, you know, well, they're equal in that respect. And therefore, there is this saying that it is not what a language can do that matters, it is what it makes easy that matters. All right. And that is why there are so many languages to begin with. So you of course, you might be familiar with C, C++, and so on. And by the way, I'm just, you know, I'm going to give a huge list of languages that almost all of them I have not programmed in. I programmed in maybe a couple of them, but most of them I haven't really programmed in, and I don't know much about them, except for, well, a few things here and there. So I'm just going to, so I may be way off in that respect. All right. But anyway, my point is just to tell you that, look, there are partly, I just want to show you that there are a number of languages focusing on a lot of things, and partly also, you may, in case you've not heard of some of them, hopefully you'll get interested in them. And anyway, it's good to realize that there is a lot of diversity in computer languages and so on. So, well, you've heard of C, and C++ should also probably been added there, but there are newer languages like Rust and Go, which I think are, you know, try to do similar things that C, you know, C is very what they call very close to the metal. You know, so it's ideal for things where you want complete control over the amount of memory usage and so on, and the time and so on. And so it gives you a lot of control, you know, for those sort of things. And I believe Rust and Go address some of the problems that might occur. You see, what is the problem actually? I mean, you know, I've just said that, you know, here's a language that gives you a lot of control over the machine. Right. So what's the problem? The problem is that programmers are human, and that when we are writing a program, those happen to be instructions for a machine. And as a result, although we think in a particular way, we have to go through a lot of effort to convert that into something that a machine can understand. So in that sense, it's close to the metal, right? And it's not something that is very what is called high level. High-level languages tend to hide a lot of the common details, but high-level languages do that sometimes at a cost. In the sense that, you know, if you had complete control, you could fine-tune things and optimize things just the way you want to. But if you don't have that much control, then of course things become complicated. Now, you might think, well, all right, well, why don't I just, you know, choose a language that has as much, where I have a lot of control over things, and I'll just do everything by manually and by hand and make sure that it's as fast as possible. Well, all that is fine for certain projects, but for as the thing gets larger and larger, these things can be really, really hard for human beings to reason about. All right, it's hard for human beings to think the way a computer works out a problem. It's hard for you to replicate that in your own mind, because computers do not have the intelligence to realize what boredom is. Okay, so they don't get bored. They can do they can just repeatedly perform a task and so on, and do the most mundane things without any problems at all. Whereas we are better suited for other ways of thinking. Okay, and so many languages try to hide these low-level details so that human beings can find it easier to program. All right, and if you find it easier to program, you can then start bothering about far more complex things. Okay, but nevertheless, these languages have their place. There are times when you need things to be optimized and so on. So I don't know much about what Rust and Go actually address in C and so on, but I'm just listing it because I happen to have heard of these languages. Well, then you have, I've clubbed them together, but they're loosely related, and especially Python is loosely related with the rest. But Bash is a scripting language which is used in Unix-like systems, in Linux and so on. And in Linux, Unix rather, it's designed so that you can glue various, as they say, it's not what the individual programs do that is as important as how you can combine them. So what they do together is what makes them very powerful. So in Linux, it's very common to, and in Unix, it's very common to focus on making tools that can be combined. And so each tool does one thing and does it very well. And on the other hand, it does it in a manner that can be combined with other programs and so on. So Bash scripting allows you to do all these things very fast. And so it's geared toward that. The syntax is geared toward that. But of course, everything has a cost. All right. So anyway, that's what it's meant for. Perl was also meant to allow, allow this kind of scripting that is popular in Linux and in Unix like this thing, operating systems, and it's much more powerful than Bash. All right. Python, on the other hand, is not necessarily very it focuses more on readability rather than being succinct. But of course, Python is also, it's not just a scripting language and a replacement for Bash and Perl. It aims to be a general purpose language, which is very popular these days for good reason. And and it has other features like object oriented and all. I think even Perl has that. But and Perl is also it's also general purpose language, but I think Perl, tends to focus on brevity, and Python on readability. Okay, so these are the differences between them. Now, C is a language that is statically typed. In other words, the types of the data are sorted out while compiling rather than during the running stage, unlike Python and Perl and so on, which are interpreted languages, same for Bash. Okay, if you programmed in C, you might find it annoying that you have to, keep mentioning the type and so on. And with Python and so on, it feels, it feels really nice that you don't have to do that. Okay, you will see later on that. Well, I'll tell you that when it comes to it, actually. Then, there's also a language like Smalltalk, which is really which I think they say that if you want to learn object-oriented programming properly, then Smalltalk is what will teach you that, and it's apparently an elegant language. Again, a language that I'm not familiar with, apart from knowing that it happens to be an elegant language which does object-oriented programming apparently in a very nice way, and so, and that the goal there was again to make it easier for humans to reason about programming and so on. Then there's Prolog. Again, I'm keeping it separate, but that's it does what's called logic programming and so on. I don't know how popular it is now, but I think at that time there was a certain kind of artificial intelligence that I think it was, at least I remember coming up in that context originally. Then there's Lisp. Lisp is a language so now we're coming closer to the family of languages that I'm going to talk about. Okay, Lisp is quite an old language, and when you look at when we look at the languages before this, maybe apart from Prolog or whatever, but these are you have this state change way of programming, where there's a certain state in the memory and you're trying to change that and so on, just like a Turing machine, for those of you familiar with it. But Lisp, on the other hand, uses what's called lambda calculus as a base, where the primitive of which you build up the entire program happens to be a function. And a function is something that just takes in an input and outputs it. All right. Now, Lisp was supposed to be quite revolutionary in its day when it started off, because I think it introduced a lot of new things. If you look at a Lisp program, it will seem very strange compared with other programming languages, because it just looks like there'll be a parentheses, and then there'll be just words separated by spaces, and then these parentheses will be nested inside other parentheses and so on. So I think there's a joke that Lisp stands for. It actually stands for List interpreter, or sorry, List processor. But there's a joke that it also stands for lots of irritating and silly parentheses or something of that sort. Okay, but there's a purpose behind that. The purpose behind that is that in Lisp, the entire program is like an expression. So it's like like when you write expressions in mathematics, you see it's like you put them in parentheses, and then the smaller ones are combined to form bigger expressions and so on. And the other thing is that because Lisp has chosen such a stripped down syntax, such a bare syntax, it is easy to build what are called macros in Lisp, where you can actually work on the Lisp program is itself written in a data type that Lisp recognizes, namely lists. All right, and therefore you can in principle write a Lisp program that can take other Lisp programs, including itself, and do something. Well, you can do that even in other languages, because it just needs to compile the text and so on. But in Lisp, it's just the parsing is already in a way done for you. Okay, and it's much easier, and that is why in Lisp, people who use it tend to talk a lot about its flexibility and about its power, and the way whenever they want a feature, they simply they can write a macro for it rather than waiting for the developers, the language, to introduce it and so on. And it gives you a lot of power. All right. Now, again, an important question is, why do we need to go any further if this is so powerful, and it's you can even use a Lisp program to modify other Lisp programs so easily and so on, then what's the problem? Well, again, the problem is exactly this, that you see, if you have a language which is very permissive, you start, you see, remember that a lot of programming is collaborative, right? I mean, you're using other people's code and all that also. Now, you might decide to be very disciplined, and you might decide to be not just disciplined, but very careful, very thorough, and so on. Although that's difficult for us to achieve at the level that sometimes is required. And in fact, anybody's program will find that even though you're trying to be very careful, there are bugs which appear anyway. All right. So therefore, it sometimes is helpful if a language makes well-chosen restrictions. The restrictions are chosen well enough so that you still find it easy to program, but the restrictions are such that, first and foremost, it allows you to, as they call it, shoot yourself in the it prevents you from shooting yourself in the foot. All right. And the other thing that it also enables is it enables the compiler to know to make assumptions about your program that a very flexible thing would not have allowed, and then it can do optimizations or do certain things for you to help you out. Okay, so having a well-chosen restrictions can be a good thing. All right. And so that's why I'm going to focus more on that. There's no point in me focusing on flexibility, because we all think it's a good thing anyway. All right. So, but anyway, before I do that, let me just introduce to some. Well, you might already have heard of them. There's Scheme, which is a dialect of Lisp. So these are all dialects of Lisp. All right. And Scheme is a dialect of Lisp, which is very which was, I think, initially developed to. By the way, you should take a look at this thing called this. It's actually there's a book available, and I think it's available for free online. It's and I think even the videos perhaps should be out of copyright now, even if they were originally, or maybe in public domain and all of that. You can check on YouTube. Which is it's called Structured Interpretation of Computer Programs. It was a course at MIT, and it was recorded. And it was many years ago, so it's very, very old. So you'll see a very old style computer and so on. But they introduce a lot of, they teach certain concepts of programming using this using Scheme, which is I think more it's a more pared down version of Lisp. All right, and so it's you should try to take a look at that also. It's a nice it's a very well acclaimed lecture series. I've only seen a small part of it, but what I saw was indeed quite interesting and nice. Common Lisp, I think, is I think the main whatever one that they use in generally. Well, or rather, it was at least for quite a while. But there's also Racket and so on now. And but I wanted to just mention this. This particular language, which is eLisp. It's actually it's a dialect of Lisp which is used by the Emacs editor. And in fact, the Emacs editor is what I use, and one of the things that you will see when I show you some code will be on the Emacs editor. Anyway, the Emacs editor, it's interesting. It's actually, I think, written in C, but what it has done is it has rather than it has a small core written in C, and then it has written a particular dialect of Lisp called eLisp. It's written an interpreter of that. And so when you want to configure Emacs, you configure it in eLisp. And because eLisp is a Turing complete language, it is so configurable that I don't know of any other software that is configured so to look so different, and which you can use it for pretty much everything. I mean, there are people who use Emacs for almost anything, reading mail and so on, and they use it all almost as an operating system. There's a joke about Emacs that it's almost an operating system because of this. But anyway, it's an interesting approach that, rather than, so although it was written in C, it's only the small core and a few primitives are written in C. Otherwise, on top of that, there's a layer of Lisp, eLisp rather, which was built specifically so that, it's something which is very versatile and that you can actually bend Emacs into whatever shape you want it to. All right. Okay. Then there's a language. I think it was, I think, done by AT&T, etc., and I think it was used by them. And I think the idea was that if there's a failure, you don't want that failure to sort of affect a lot of other things. You don't want everything to break down, and so that's how that's, I think, why it came up in the first place. But let me come to the languages that we are interested in, the family that we're interested in. This is ML. ML, I think, so nowadays ML stands for, machine learning and so on, but this has got nothing to do with machine learning. This was, I think it stood for meta language. And I won't talk much about ML and so on, except that because a lot of its concepts have been borrowed, have been incorporated by Haskell, and so it'll come up there anyway. But you should know that although Haskell has taken a lot from ML, it does not mean that ML is replaced by Haskell. Far from it. ML, and in fact its modern dialect OCaml, which is popular now, are also very good languages. They have in fact made certain choices which are different from Haskell, which have their own advantages and which are worth looking at also. And in fact, Haskell tends to be a little more experimental and so on, but OCaml, etc., probably more suited for, safer for certain practical purposes. Okay, whereas Haskell tends to keep the, it wants to be practical, but there are certain principles that it wants to be a bit, it wants to explore a bit and so on. So it wants to be a little experimental and so on. Okay, so that is its main goal, and it does a pretty good job at being practical despite that. But nevertheless, there are certain things one should be a little careful about. All right, so that's Haskell, and that's what I will use Haskell as a means to introduce functional programming. Okay, I think I'm spending too much time on all of this, so I'll just quickly leave you with a list of languages which are also worth looking at, although I think they are harder to understand and so on. Again, I haven't gone into them, but I know that these languages are, I think these languages are not very general purpose. I don't think people write general purpose programs in them, but Coq, for instance, is a theorem prover. So it allows you to write proofs of, it's a theorem prover and even a theorem checker, actually, first and foremost. And it allows you to write, it allows you to verify proofs written in mathematics and so on. You have to write in a certain way, and it will confirm whether the proof is actually correct and so on. There are no errors in that proof. So, and Agdon and Idris or Idris, I don't know how it's pronounced. These are all, they have a feature called dependently typed. So I won't go into what it is actually, and in fact, I don't think I have a good feel for it either, or rather at least how it's used much and so on. But nevertheless, you can read about it if you wish to. All right, so anyway, now let's come to the main part of the talk, which is functional programming, and especially, Haskell. So I should also say this, that I'm not trying to teach you Haskell. In fact, at the end of this talk, you won't even know how to write a hello world program in Haskell, even though you'll be exposed to a lot of code in Haskell. All right. So I'm not even bothered to be, about making sure that all the pieces fit together. It's just a walk in the park and, showing you various things. And if you're interested, later on, you can consolidate all of these things by reading some of the references that I have, that I'll outline at the end. All right. Well, I should first, tell you what all is done in Haskell so that you get interested in it in the first place. So one of the very famous programs written in Haskell is Xmonad. I use Xmonad as my window manager. It's a window manager. And one of the reasons you see that in all my software, it does not have any window decorations at all. The maximum screen estate. There's no cancel button and so on. There's no border around it and all that. Because Xmonad is meant for people who like to use the keyboard rather than the mouse. And it's what is called a tiling window manager. So maybe I can give you a bit of a demonstration of this. So you see, if it'll tile all my windows so that it's, let's say you're doing something in LaTeX, right? So you might want to keep your edit on one side, the PDF on the other side, and so on. So it helps to tile things, and you might want to tile it in various ways. So this is what these are called tiling window managers. And Xmonad is quite small. I use it because, well, I like it. And it's very configurable and all that. But apart from that, it's very low on resources. My computer runs much faster with it than with the usual Unity interface or any of the other interfaces and that I've tried out. And apart from that, it's also very reliable. And I think a lot of these features have to do with Haskell. Okay, it's very. I haven't at all encountered a bug in my years of using Xmonad. Okay, I've never had a crash because of Xmonad. So. I hope today is not the first day that happens anyway. That'll be embarrassing, but anyway. Then there's this other software called Pandoc. Pandoc is what is called a document converter. And it's popular because it's one of those, it's a command line utility, but it's very powerful and it can convert, it can convert any, quite a few formats to other formats. And largely people would like to use Markdown, and then you can convert that into LaTeX, you can convert that into HTML, and so on. Pandoc is used as a backend for another thing called Haskell. Haskell is so it's actually it's a replica. It's not well. It's not really a clone. It isn't a clone, but it's inspired by. It's a version. It's a Haskell version of a program written, I think, in Ruby called Jekyll. And in fact, GitHub uses Jekyll if you want to use GitHub Pages and so on. But what Jekyll does is it allows you to write static pages in a very organized manner, in a very Unix-like manner, by separating the relevant things in the right directories and so on. And it's a kind of manner that people who are used to Unix style would like to use. And then when you run that, it creates a website, and it takes care of all the dirty work of putting the links in the right place. People write blogs using that particular thing. So Haskell is the Haskell version of that. I have used it for my websites for courses, and so I just put the exercise in the right directory, and then I run Haskell, and it takes care of linking them wherever I want to, and so on, and things like that. So I have complete control over everything. Okay, and unlike, for instance, if I do things on WordPress and so on, there you have certain templates and so on, and it has its advantages. I mean, but if you're familiar with Haskell and you can configure things in Haskell, then you would probably prefer using something like this. Okay. Anyway, it's just one of the options available, not necessarily the best one. It depends on how you like to do things. Then there is this interesting thing called Utopy. Utopy is it uses Haskell for music in a very interesting way. You see, maybe I can tell you what. So there's this program in Java, written in Java, called JFugue. Now, a fugue is, for those of you who are not familiar with this particular term, again, I'm not at all an expert in this, but I just know, I'm basically telling you whatever I know about it, which is that, you see, I think Bach used to write a number of fugues, and one of the, one of the goals, or rather, it's actually an exploration in harmony. So the idea is that, you take a small motif, right? You take a small string of notes which has an entity on its own, and you perform certain transformations on them which are very mathematical. So you can invert them, you can actually reverse them, and so on. And and then what you do is you take these little combinations and so on, and sometimes minor variations, and you play them a lot simultaneously, but with some delay. So it's a delicate thing, right? I mean, because your notes will clash with each other, and you've got to choose the motif in such a way that these notes, when they're clashing, are harmonious. And anyway, so why am I bringing up all this over here? Because in Utopy, in fugues and all of that, you take a motif and you apply these transformations. You either move all the notes up few semitones, or you invert them, or you reverse them, and so on, and things like that. And so it lends itself a lot to a functional style of programming. And so what you can do in Utopy is you can actually program in Haskell and generate fugues like this. If you want to experiment with things, you can define a particular subject, and rather than manually putting all the notes, you can experiment with, say, supposing I perform this particular combination of things, how does it sound? Now, supposing I keep the combination as it is in all its complexity, but I only change the subject, and I alter the subject. Let me see how it sounds, and so on. Okay. What is interesting is if you, so Utopy, by the way, there's a book also called Haskell School of Music. And if you actually read that book, interestingly, that book tries to teach you Haskell by developing this module, or this program called Utopy. And you will learn a lot of things as the book shows you how to develop it and so on. And you will see how easy it is to actually program such a thing. You would normally think this is something that is rather complicated, especially converting it into MIDI files and so on, into MIDI rather. But all of this is actually quite easy because of a few choices that Haskell has made. Okay, then there is this other thing called a program called Haskell Diagrams. This is actually, it's not a program, it's a library, it's a Haskell library. It's not a program, yet I bring it up because, it does, this is the website. I'll give you a link. Well, I've actually posted the link over here. Right, that's correct. So if you look at the code, for instance, by the way, speaking of fugues, Escher's, you might have heard of this painter called Escher. And in fact, there's this book called Gödel, Escher, and Bach, which tries to talk, which brings up Fuchs quite a lot and also talks about Escher's paintings. Now, Escher's paintings tend to be similar, tend to be a counterpart of what I described with Fuchs. That is, you take a certain kind of a small, you paint a small image of whatever certain subject or whatever, and then you take various combinations of it, and and these combinations together give you something nice and complicated. And let me see. I think in this there is in the gallery, or I think they have probably shown an example. Anyway, probably not. Yes, well, this is one of them. I think this is something that would be like that. Anyway, I'll also give you another reference of a video which will talk about these. Oh, this is one of them. This is one of them. This is, I think, something similar to what Escher has drawn. And you see the code over here. By the way, this code is written in what is called literate Haskell. So the actual code are these blocks that you see over here, and it's quite, for something as complicated as this, except for, drawing that basic thing, that's where all the effort will go in. But otherwise, most of the times you will find that the code is actually quite short, you see. And just to give you one more example, in this, in this chess board that you see over here, I mean, you may not understand the code as of now because you're probably not yet familiar with Haskell syntax, but I'll tell you how this chessboard was actually drawn in the code. It's quite simple, actually. And what it does is it simply you take a black square and you take a white square. All right, what do I mean by that? You take an image of these things, okay, represented as a data type. All right, see, don't bother about the details over here. What I wanted to get a feel for is that the way we are drawing a chessboard in Haskell is pretty faithful. The code is very faithful to how we would think about it naturally anyway. And there's not much of intermediate work of transforming this thing into a way that, you have to transform the syntax, certainly. But the syntax is very faithful to the way we are thinking about things, rather than actually having to change the very way we are, the very approach to this particular problem. So essentially what you can do is you take a black square and you take a white square, and you simply create you take a list of a black square and a white square, and then you simply take infinitely many copies of them. Okay, so they alternate, and you take infinitely many copies. How can you possibly take infinitely many copies? Well, Haskell has a feature called lazy evaluation, which allows that. I'll come to it later. Well, it's lazy by default. So in Haskell, all this is very easy. And then what you do is you take this infinite one and you chop it in chunks of 8. All right, and then you take this list of lists that you get after you chopped it up, and what you do is you simply combine. You simply, for each and every one of these infinite lists within the list, you concatenate them horizontally, and so you get the rows. And after you do that, you then choose 8 of them, okay, and you concatenate the rest. All right. So you see, it sounds intriguing, right? I mean, it sounds the way you would like to do things anyway. You just want to place them one after the other, and so there are all these operators that diagrams defines, which makes all this very natural, and it makes this code quite natural and easy to reason about. All right. So and the other thing is there's this thing called detechify. Some of you might have used it, where if you don't know what the code is for a particular LaTeX symbol, what you could do is you could draw it on this website. It allows you to draw it, and then it will suggest close enough codes for that. So I haven't used it much myself, but I recently learned that it uses Haskell in the back end. And then there is this thing called HLedger. There is a famous program in command line Linux, which is called Ledger, which allows you to do accounts and things like that. And HLedger is the Haskell version of it. It's also pretty popular. And then there is Darks. If you've used a version control system like Git, then Darks is a counterpart of that. However, Darks has not been all that successful because, well, it's old, it is quite old, but, and I don't think it's I don't know for sure, but I don't know whether it's been maintained very well, but Git is much more, much faster and so on. And, but, you know, I once saw a statement saying that, you know, we love darks, but use Git. In other words, you know, people, at least whoever made that statement was claiming that darks is very elegant in its design and so on. I don't know much about it, so I won't talk much about it. All right. So, all right. So, any questions at this stage? Any questions? So, how much time have I already spent? I don't want to spend too much of time. Okay. Oh God, I seem to spend a lot of time already on the preliminaries. Anyway, so okay. Finally, I just want to you know, whet your appetite with something interesting over here. Here is a short program which implements, it's not mine, by the way, I've taken it from this particular website called Power Series, and well, web page rather, and you should take a look at it. And it's what it essentially does is the following. It implements infinite power series in Haskell. Okay, and it does that roughly by you know, power series is characterized by its list of coefficients, and so that's how it does it. All right, it basically implements a list of coefficients. But I want you to keep in mind the following thing: Haskell is a general purpose language. All right, it was never meant to be. It was never built for something like Mathematica or something of that sort. So it's pretty remarkable that we can do something like this, implement power series in code which is so short. If you want it to be more efficient, if you actually don't care about efficiency, functions like product of power series, sum of power series are just a single line. And in fact, this big part of the code that you see over here is only because of because one is trying to render it better. What I mean by render it better is that you know, if a number is 5/1, a rational number, if a particular coefficient is 5/1, you want to write it as 5 rather than 5/1, right? Or if it's x to the power of 1, you don't want the power 1 to be there. So it's just to make things even closer to how we're used to it that, you know, so much of code has gone into it. But otherwise, it's pretty short, right? And here's something very interesting. You look at this. EXPS stands for the exponential power series. Okay, do you know how this exponential power series is defined? It's on the left over here. If you can see my mouse over here, do you know what it's defined as? It's defined as exponent is equal to 1 plus integrate exponent. It seems to be self-referential, right? I mean, it seems to be referring to itself. How is this happening? And yet, that is all the code that I need in order to get this power series. And it actually contains infinitely many. The only reason I'm not showing you all the coefficients is because, well, it's never going to end. Okay, that's why there are only 10 of them, the terms that are chosen and displayed to you. Even more interesting, look at the sign of x. What is sign of x defined as? Sign of x is defined as the, well, it should be minus of sign. It's actually minus, there should be minus sign, integral of cosine. And cosine is defined as 1 minus integral of sine. Okay, and so, again, you know, they're referring to each other over here, right? And yet we are able to, and that's all it takes to define it. So this brings us to a very important point. You see, when I think in the early days of computer programming also, there was a lot of hope that one could try to make things more declarative. That means you declare, you sort of specify what something means rather than how to implement it. And ideally, the program or whatever the language should be such that it kind of deduces that. Well, we haven't got there yet. It's not close, but not even close, perhaps. But you know, all of these things get you somewhat close, and it's interesting to see that you know how easy it is to implement this kind of a thing, right? So this is and so, you know, the question to ask is, what choices has Haskell made, which is actually a general purpose language, which was certainly not built for this purpose, which allows you to do things like this. It allows you to represent power series in this manner. I can, you know, let's look at 1 plus x squared. You see, and I get 1 plus 2x plus x squared. What is remarkable about this? What is remarkable about this is that the code for all of that is over here. So what allows Haskell to, even though we're taking a very small thing, we're taking only power series, okay? That's all we're taking. We're not going through all the things that Mathematica does. Yet if I asked you to implement power series in C, it would be a scary thing to do, right? It would sound like a complicated thing to do. And yet here we are able to use syntax, which is very natural to us. I'm able to say 1 plus x to the power of 2. And it gives me something very nice over here. So what is it about Haskell? A general purpose language, yet when I want to implement something like power series, it is so close to what we expect that it seems as though Haskell was developed for a different purpose altogether. It was like Mathematica, at least in this case, all right? So I feel that it has made some very interesting choices in that sense, and those are what I'm going to, outline. Okay, so anyway, enough of all this. Now, I'll actually skip this particular slide because I think it's a little confusing and I've already run short of time. Now I'm going to come to the main part of the talk, the part which involves code now, after giving you a lot of examples and so on, which hopefully you'll find interesting enough to follow the rest of this and go through the trouble. So let me, you see, suppose, now, one piece of advice, when you are following this part of it, whatever you know from other languages, whatever you may know, forget about it. If ever the question arises in your mind, is this related to so-and-so term that was used in some other language? Well, it is safe to assume that the answer is no. Okay? Forget about the question completely, forget about the other language completely. One of the hardest, one of the great difficulties in learning something like functional programming can be bringing in all that baggage. And so you expect it to behave like that, but it behaves completely different. So just forget about that. It's actually quite easy. All right. But allow yourself to just soak in whatever is being explained rather than trying to compare it with something else. Okay. You can do that after you're familiar with everything. All right. So let's start with something like this. So let's say what can you do on a calculator? You have some primitive functions like square and plus and multiplication and so on. And you can do things like this, 2 squared plus 5 squared and so on. Now, what you can do in Haskell is you can give it a name. Z1 is equal to this. Now notice, I'm calling it a name and not calling it a variable. There's a very good reason for that, all right? If afterwards you write something like Z1 is equal to 0, and you try to compile the program, Haskell is going to complain very loudly. The compiler is going to complain very loudly, and it will say something like, well, not in so many words, but it's going to say that, well, on the one hand, you're claiming Z1 is this, on the one hand, you're claiming Z1 is this. What do you mean, right? How can one thing be two things at one time? Okay, so it's not a variable, okay? Not like variables in other languages, all right? So think of it as just a name. I'm not going into the actual terms for all these kind of things. As I said, my goal is not to teach you Haskell. All right. So let's say you have Z2 is equal to something like this, a similar expression. All right. Now, well, a calculator, you've got to type in these things over and over again. But, you might notice the following thing. You might say that, look, everything else is the same. The only thing that's changing over here is the 5 is changing to a 7. Okay, so why don't I abstract that out so that I don't have to keep writing the expression over and over again? So what I do is I can define this function g of y is equal to 2 squared plus y squared. Now let me explain this syntax because this is going to appear over and over again. What have we done? What we've done is instead of calling it Z2, we've called it something general like G, just like in mathematics, we have F and G and so on. You can actually give longer names. I'm just choosing something simple because I don't want to give it something longer. All right. So, and whenever you want to generalize something, you see a particular part of the code and you want to generalize it, right? So in other words, you wanted to take other values also. What you could do is you could simply give it a variable, all right? And that variable will come on the left-hand side like this. So you have g of y is equal to this, all right? Now, in other languages, functions are usually, not all other languages, but some of them, many of them actually, functions are usually denoted with, the name of the function, parentheses, and then you put in the arguments. In Haskell, there is that parenthesis, it's based on something more fundamental, and that if you write a function that way, it is possible to write it in that way in Haskell too, but it has a different meaning altogether. Maybe if I have time, I'll explain that. But in Haskell, you don't need to use parentheses at all, because functions are so ubiquitous in Haskell, because you use it so often, and that's pretty much what you're using almost all the time. Because of that, Haskell tries to make the syntax as lightweight as possible. So it's name of the function, first argument, space, first argument, space, second argument, space, third argument, and so on. All right, all of that. Okay, so let me give you an example with two arguments. So here I'm also generalizing the 2 squared. So I've got x over there, and so I have f of xy is equal to x squared plus y squared. How do you apply? So by the way, notice one more thing. Z1 can be written as G5 and Z2 can be written as G7, right? But observe one more thing. My definition of G comes after the point where I've used it. Okay, and this is another thing that might sound a bit surprising in Haskell. In Haskell, you can define your functions any way you want. You don't necessarily have to define it before the point where you've used it. All right, and in Haskell, you're pretty much writing only functions. So in other words, you can take your blocks of functions which make up your entire program, and you can rearrange them and put them in any order you want. It does not matter. Okay, why? I'll explain it. I'll explain that a bit later. But all right, now let's look at g of y. What is g of y? I can define it in terms of f, right? G of y is equal to f of 2y. Now, here's another interesting feature of Haskell, which at first may seem it may not seem very useful. It may seem like something, well, it's nicer to have it, but it's not all that useful, but actually does turn out to be extremely useful, even if it's mainly just syntax. And in fact, its use is not confined to just that. It's called currying. You see, when you have g of y is equal to f of 2y, you don't need the y over here. You can just write g is equal to f of 2. Okay, and the reason behind that is because in Haskell, functions which take multiple arguments, which seem to take multiple arguments, are actually functions that take one argument alone. Okay, what they do is when you plug in the first argument, you can think of these arguments as sort of, things, parameters that can vary. And once you plugged in that argument, so let's say you plug in a 2 inside this x, right? The y can still vary. So functions with 2 arguments, for instance, are things where they take the first argument and output a function which takes only 1 argument. A function which takes 3 arguments, for instance, is something that will take when you fill in the first argument, it will output a function that takes 2 arguments. What does that mean? That means that it is a function that when you fill in an argument, it will output another function which takes which then takes 1 argument. So in a certain sense, all functions take only 1 argument. It's just that they may take 1 argument, and they output either functions that take 1 argument or functions that output functions that take 1 argument. All right. Why, you may ask? Well, it gives a certain unity. All right. There's a particular package called Quick Check and so on, and when you see it, you wonder how do you do such a thing in Haskell? How is it even possible to do such a thing in Haskell? And you realize it's because of the fact that all functions are really single argument things. So you can do some magic which works for all functions which are just which take 1 argument as input and output something, and it works for all of them. Okay, never mind if you don't understand what that means. But apart from that, you see, a lot of times in functional programming, you output functions a lot. Let me give you an example. Supposing you take a list, right? And you take a function which, a list of something, let's say a list of integers, and you take another function which acts on an integer and outputs another integer. You might want to apply that function on every element of the list. So you have what is called a map function. So map will take the function f, and it will take the list, and it will apply f to every element. So you can either think of it as a 2-argument function, or you can think of map as something which will take f and output a function which now acts on lists and outputs a list. All right. So converting functions into other functions is very common. And even in a language like Lisp, the way you have to do that is to actually define the function as a value inside and then return it. In Haskell, you don't, you can just say that, look, well, I just give it extra arguments, that's all. Okay, and you can arrange it that way. All right, anyway, so it's useful. Another thing I want you to notice about the syntax is this equal to sign. This is a very honest syntax. What this means is that wherever you see 2 squared plus y squared, you can safely, if you see 2 squared plus 7 squared, you can safely remove that expression from your program and replace it with g of 7 and vice versa. Wherever you see g of something, you can replace it with what is on the right-hand side. Whenever you see the right-hand side appearing, you can safely replace it with what is on the left-hand side. You might think, well, that's what we can do in any language, right? Not really. In ordinary languages, functions can have what are called side effects. They might be looking at a global variable and so on. And then where the function is appearing is very important because if it's appearing before putting in a certain value, before some alteration of the global variable, it'll output something very different, all right? So, but in Haskell, since it does not allow that, which made it's again a well-chosen restriction, that is why you have this particular thing. Okay. Now I want to emphasize a few more things with this example. I call this NRM, mainly meaning norm, but it's not strictly a norm because a norm should actually apply to a vector rather than just taking. But here, what we're doing is we're just taking two. Forget why it's called that. All right, it's just called something NRM. And what does it do? It takes 2 arguments, x and y, and it gives you the square root of the sum of the squares of them. All right. Now, what did we learn about abstracting out? We said that if we ever wanted to generalize something on the right-hand side, what we can do is we can give it a name and we can bring it on the left-hand side as an argument. All right. So let's say the square root. Supposing I want the square root to be generalized. So maybe because I also want to take the cube of these sums of the squares, the cube root of it, or whatever I want to do. So what I will do is I will replace square root, which is a concrete function, by this name and put that as a parameter on the left-hand side. Okay, and now the original function can be retired. So GNRM is, you can think of it as general NRM, and I can define the original. Oh, this should be SQRT. Is a type over there. So the original NRM can be written in terms of GNRM. Let's take this further. I can. What about the plus sign? Okay. Now here is, you see, Haskell tries to do things in a way that you can use a very mathematical like expressions, so where you use operators in mathematics. So Haskell deals a lot with expressions, okay, even when you would not, even beyond mathematical things and so on. So you would want expressions to be combined and so on, and so operators are very important over there. They appear quite often, and so in Haskell, if you put any function which you've already defined, if you put it within backticks like this, it becomes an operator. So then, rather than prefix notation, where it looks for its arguments after the name, now it will look for 1 argument to the left, 1 argument to the right. What if it has more arguments than just 2? Well, you know that then it will output a function with the other arguments left as it is. All right. So, and another thing about Haskell syntax is that if you take something which is already an operator, and if you use symbols rather than alphanumeric characters, only symbols, what Haskell by default treats it as an operator. But if you put it within parentheses like this, like the plus sign is, then it gives it a prefix notation. So for instance, parentheses plus 2, 3 is the same as 2 plus 3. All right. So this is just a bit of syntax, which will appear sometime. So just remember this, that if I use only symbols to define a function, Haskell treats it as an operator, unless I wrap it within parentheses, in which case it is treated like an ordinary function where the arguments appear. Well, they're all ordinary functions, but it's just about the placement of the arguments. Okay. So there's just some syntax, sugar, which is provided to us. All right, and now there's this ridiculously general norm where I'm even generalizing the square. All right, so that's simple to understand. Okay, so I just thought I'd complete the whole thing. And so this is this very ridiculous kind of a thing. So what have we learned over here? There's another thing you would have noticed already, which is very different from C. And that is that functions are data. Okay, otherwise you think of functions acting on data and data separate from functions. But functions are data also. In other words, you can use functions to act upon functions. You can, just like you have variables in which you can fill in data, you can also fill in functions. And this is why I'm able to not just abstract out 5 and 7 as in the previous case, I'm also able to abstract out actual functions, okay? And so I have functions which take as arguments other functions and output another function or output an expression and so on. So functions are data, and this unity allows a lot of flexibility. What you can do for data, you can do for functions. In fact, you can think of ordinary data, let's say you have Z1, Z2, or whatever, as functions which take no arguments. That's just a way of thinking about it, all right? But you can think of it that way. All right, so what I'm going to do right now is I'm going to try to define, you see, as of now, I've defined just the function, okay? Now, what I'm going to do is I'm going to try to be as conservative as possible and try to add very little to my language and try to make do with what I have as much as possible. And anytime I want to add something, I'll try to be as minimal as possible. What I'm trying to show you is that very few primitives are required to do anything you want, all right? More complicated things are combinations of these primitives, all right? In fact, using these primitives, you combine them to form less general and less complicated things, and then you combine those to get higher level things and so on. And so this is called composability. You see, it's always good if things are composable. That is, you're able to combine things and build more complicated things by combinations of simpler things. Okay, and another comment that I want to make is that a function, you see, I haven't even defined it formally, and I don't want to, but you've already got a feel for it. It takes a few arguments and outputs something. In fact, it always takes one argument and outputs an output, right? But as I said, the output could be a function that takes something else, and that's how you get multiple arguments. So what is how can functions be, pretty much what you need? Well, think about it. Almost everything is that you can think of, you can write it in terms of a function. For instance, as I said, you want to build more complicated things out of simpler things by combining simpler things. Well, even the combination, the thing that will do the combining for you, is also a function. It will take the simpler pieces and combine them and make something bigger. Okay. Supposing you take let's say a tuple, as you've seen in Python. Supposing you're peeking in a particular part of the tuple, right? In object-oriented, you're familiar with this sort of syntax where you use a dot and then you put the name of that particular part of the data type and so on. Well, what are you doing? You're taking a big complicated data type and you're trying to see a small component of it. So the input is the big thing, the output is the small component. So it's also a function, right? And if you really think about it, supposing you're trying to solve any problem, the way and I like to think about it this way, that when you're thinking about Turing machines and all that, you're thinking about things very linearly, right? Step by step. This is what you're going to do. This is how you're going to change the state. This is what you're going to declare. And there's one step after another. Okay. But when you're actually thinking about things the way we think about them, it's a little closer, I feel, but I may be wrong about this. But this is the way I look at it, is that it's a little closer to the functional style. Because what happens when you're trying to solve a problem? Well, you examine something, whatever you're trying to compute or whatever, and then you examine you start examining pieces of it, right? And then what do? Using those pieces, examining those pieces means using a function. You take the big thing and you split it up into its components. Then you start looking at those pieces combined together in one unit. So you need something which will combine them into one unit. Right? Sometimes you look at a certain subset of information on its own. You think of it as one single unit, and then what do? You take these pieces of information and then you use and then you use that to deduce something else, and then you use that to deduce something else, and so on and so on. And so there's a whole, and sometimes so the way you imagine it, there's some input, and then it's being branched off into various pieces and so on. Those pieces are then combined together, and then it's like a circuit, like some sort of circuit, and all sorts of things are going on. And then in the end, all that is collected and put into the final output, and then finally displayed. Now, I know I'm being very, very vague over here. I'm just trying to give you some notion of how I imagine these sort of things. But the point is that there's a very non-linear way of, you approach this in a very non-linear manner. And you also realize that if you think about things, you can, anything that you're doing, any kind of computation, you can think about it as a function. And if you want to understand how to make sense of that function, you can think about its composition of simpler functions. And the thing that does the composition is also a function, okay? And the simpler functions can themselves be thought of combinations of simpler functions and so on. And you keep doing that till you get very simple pieces that are primitive enough that, you know, there's no more understanding required, and you can just use the primitive functions. All right. So if I've been vague over here, well, I intended to. All right. So now, well, so far I've just rambled on about why functions are, why lots of things are functions if you really look at it. But how do you do certain things that you do in an ordinary, you know, the languages you're familiar with? Well, looping is one of the things, right? Now, supposing I want to understand what the factorial is, okay? Recursion, you see, in functional languages, you can't have loops. Why can't you have loops, really? Well, actually, in Haskell, you do have certain things that you could call loops. Well, you know, I don't want to go into all of that, but, you know, you can replicate what you've done over there in what are called, well, anyway, let me not get into all of that anyway. The point is that loops, inherently, what do? You take I is equal to something, and as it's running through the loop, that I is varying, it's changing, right? Now, you can't have that in Haskell, all right? It's, you know, variables here, what are called immutable. Once they're defined, you can't change them, okay? At first, it might seem like, well, you know, you're tying your hands up. There are certain things you can't do then. But no, you can. You can do everything. All right. But the point is that in a for loop, you're varying that. And so that's why you can't have a for loop-like thing over here. But you have recursion. Okay. What does that mean? In other words, you can use the function in its own definition. Okay. So here's how I define factorial. I define the factorial as, well, factorial of 1 is simply 1, and factorial of n is equal to n times the factorial of n minus 1. What's the advantage of n minus 1? Well, it's simpler. So I have defined factorial. I have reduced the definition of factorial to something simpler. And in that sense, this is what makes using recursion very expressive. It's very easy to express it because all you do is when you want to perform some task, you simply ask yourself this question: Can I get the answer by if I knew something, a simpler version of the input? Okay, if I knew something slightly simpler, just one step simpler, then. And if I knew the answer to that one, would I get the answer to this one? So for instance, if I knew the answer to factorial n minus 1, would I be able to compute factorial n very easily? And the answer is yes, you can do that. And this is the definition. Okay. You might, I mean, some of you may be uncomfortable with this. You might think, well, isn't this going to blow up the stack? I mean, you know, to compute factorial n, it'll first have to multiply n times factorial n minus 1. Okay, then factorial n minus 1 has to be computed. Only then can it compute the multiplication. But to do that, it'll have to write factorial n minus 1 as n minus 1 times factorial n minus 2. And as you can see, it's going deeper and deeper and deeper, and you know, and it's using up a lot of memory before it starts collecting everything. Whereas if you use a loop, well, you don't run into this problem. And the answer is correct. Yes, it is. Well, so how do we do this without loops? Well, we use what is called tail recursion, which actually then does what the loop does using recursion on its own. But let me explain what it does. So let's look at this one. Factorial n is simply a particular function that I'm going to define below. And by the way, I'm introducing new syntax over here, but it's pretty... you can understand it quite easily. By the way, if you don't understand something, you can let me know. All right, just interrupt me. So it's fact loop, which I'm going to define, and it's simply I'm simply defining it. I'll explain the one later on. Okay, what does fact loop do? Well, this k that you see is something like your I, which is going from 1 to n. Okay, so you can see what is happening. As long as k is less than n, you use this function called factorial loop, and what you do is you multiply k with what was already there. Okay. By the way, there's a mistake over here. These two should be reversed. It should be 1n. Sorry about that. It should be 1n. But anyway, the point is, you see, this expression, it is recursive, right? It's recursive over here because you can see the fact loop is recursive. What does it do? As long as k, and you can read this as follows, that as long as k, if k is less than or equal to n, in that case, simply multiply the k with p and apply fact loop to that, and then also to k plus 1. So increase k plus 1. And then fact loop will now use a new set of arguments. Instead of p and k, it will now use k times p and check whether k times p is less than n, and k plus 1 is less than n, and if it is less than n, then it will, to k times p, it will multiply k plus 1, and so you get k plus 1 times. So it's keeping a track in the arguments of that variable I, and that is why it does not need to it's playing the counterpart of the variable I. So it does not need to mutate that. It's taking as an input k and p, and it's outputting a function where it's taking the updated versions of k and p and providing it to that particular function. So as a result, but the important thing with this recursion is that the last thing that you do over here happens to be fact loop itself. You're not multiplying it with something like you were doing in the previous one. And as a result, once you have got fact loop of k times p times k plus 1, you know the compiler no longer needs to remember how it got that. Okay, and therefore it can optimize it away. So this is called tail call optimization, which many of these languages which allow this optimization then allow you this convenient method of using tail recursion. Now, I haven't, okay, never mind if you do not understand the details again. What you should realize is that I have not added anything to the language, and I've been able to replicate loops. Okay, so that should give you a feel for why I'm inching closer to doing everything that you can with an ordinary language. Now, another interesting thing is that if you look at, this is just a small aside. Notice the exclamation marks that I have put in over here. I'll comment on that later, but the reason is because Haskell is what is called a lazy language. In fact, it's not, the correct term is non-strict, but the differences between the two terms are subtle, and let's not go into that. But it's commonly called just lazy language. In fact, the compiler, I believe, the most common compiler uses lazy evaluation anyway. And what that means is, you see, in any other language, when you are applying a function to its arguments, the argument may be the output of some function itself. So for instance, here the arguments are the output of a function. It's the output of a product of k times p. Here it's the output of k with added to 1, right? Any other language will instantly, not any other language, but non-strict languages, what are called strict or non-lazy languages, will simply evaluate these arguments first, and then feed it into and then compute the top function, which is fact loop, etc. in this case. In Haskell, it will not do that. Haskell's evaluation strategy is postpone the evaluation until it is required. So for instance, if something is not needed at all during the running of the program, it will never be evaluated. Okay, and once something is evaluated, and the other thing is that if it is needed again, the evaluation is done only once, nevertheless. All right. So first and foremost, it will evaluate only if it's required, and on the other hand, if it is required more than once, it will not be evaluated each time it is required. It will be evaluated only once and stored in the memory, and that's all. Okay. What is the use of this? Well, it has a lot of uses. And why is Haskell one of the rare languages that does it? Well, because Haskell imposes what is called a purely functional language. It imposes what is called referential transparency. What that means is that in Haskell, functions are honest functions. If you give it an input, it will give out an output like any other function. However, it is exactly like a mathematical function in the sense that if you give it the same input, if you gave the same function the same input, you will get the same output no matter where that function is situated in the program. Okay? And what this means is that the compiler has certain guarantees and that it can dare to do certain things to your code that other languages, non-pure functional languages cannot do. Okay, and as a result, it can dare to be lazy because only when you have pure functions, and you may not understand the reason why by just telling you this, but only with pure functions is it safer to have a lazy evaluation strategy. Right? Otherwise, it becomes very, very hard to reason about it because you don't know when it's going to be evaluated. When I said actually it's safe, I didn't give you the full story. In Haskell, what happens is that if the Haskell compiler can confirm that that this particular value is going to be required always, irrespective of how the program proceeds, it is ultimately going to be required, it may decide to evaluate it there and then. So the correct thing to say is that in Haskell, you cannot make assumptions about when something will be evaluated. The compiler will try to evaluate things based on what it feels is the best outcome. However, you cannot rely on it. But Haskell gives you a way of saying, look, no, I want you to evaluate this. When you're evaluating this, I do want you to evaluate this first. All right. So, for instance, these exclamation marks are basically telling the compiler that when you're evaluating fact loop, whenever you do that, please ensure that you evaluate P first, because there is an exclamation mark before it. And if there's an exclamation mark before K, then also evaluate K before doing that. All right. So in this way, you can disable lazy evaluation. All right. But I must say that lazy evaluation is a bit of a controversial topic in Haskell because of the fact that it does lead to, it does make it harder to reason about space. There are certain best practices which can mitigate problems. And in fact, when I follow those practices, I've never had a problem, at least to the level that I want to avoid. I don't want things to blow up. And that I've been able to avoid. What I might not have been able to avoid, and which I wasn't even concerned about, is whether instead of using maybe so much memory, I actually, for this particular small part of the program, I actually used twice than was necessary. I wasn't concerned about that anyway, because I have enough of RAM for that. All I don't want is that as the program progresses, I don't want things to blow up. So that is easier to take care of as long as there are certain best practices. It's not an ideal situation, but these are trade-offs. Okay, you make a choice. It has certain advantages, it has certain disadvantages. Certain languages have chosen one way, certain languages have chosen the other. And what has happened is that because of these problems, in each language, because people try to then innovate and come up with ways of bypassing them. And in Haskell too, there have been certain innovations in this regard. Anyway, so what have we done until now? We have sort of incorporated loops, but we still don't have branching. In fact, we still don't even have Boolean. Okay. Now, Haskell allows you to define your own data types in a manner that is called what are called algebraic data types. Okay. Why is the term algebraic? Because you can combine simpler ones to make more complicated ones. Now, while I'm doing this, some of you who are familiar with C will say, oh yeah, well, if you do this in C, you can use pointers and all for some of these things. And the answer is yes, but there you have to bother about the pointers. You've got to actually do all the manual work. Here, you don't have to do all of that. Okay, the syntax is very clean, and all of that is done behind the scenes so that you don't have to bother about it at all. Okay, so let's try to look at Boolean. Okay, what do I need in Boolean? I need two values. So you can think of this as defining a set. There are no curly braces, which is traditional, because one is just trying to be light with syntax over here. So the syntax is data, Boolean. I'm defining bool as a data type, right? And that is equal to the set consisting of true and false. Okay, you'll see why there's no set notation over here. Okay, so and also why I'm not using comma. All right, it's perhaps closer to think of this as a union of singletons, or even better, just think of it this way: the data bool is either a true or a false. You know that the pipe is sometimes used as an or symbol, so you can think of it as either true or false. That's what Boolean data is. What is true and false? Well, they're just tags as of now. Think of them as just tags. I'm not necessarily being very accurate. I'm not bothered about that yet. All right. As I said, this is only to get you to show you how clean things are. You can then look up the precise definitions and so on. Okay. Now I want to define the not function. What does the not function do? Well, if I give it a true, it outputs a false. So I define not of true is equal to false. Well, I seem to have skipped out something over here. I'm so sorry. I don't know how that, I might have overwritten it. So, right. And I also need this one. False is equal to true. I'm sorry, it might take a little while for it to compile. Okay. So, what is happening is look at the syntax over here, right? I mean, a Boolean consists of either a true or a false. And all I have done is, I've said that, all I have done is the following. I've said that not true is equal to false. And I have used the same function name and I've also applied it to false. And I've said not false is equal to true. What you're seeing over here is what is called pattern matching. It may seem like it's very trivial, but it's interesting that you can, using this trivial thing, you can achieve so much and you can build so much on top of it, right? So what is it doing? What will happen is when you apply not to X, it will check whether X matches with true. Okay, literally matches. It will just check whether X happens to be the same tag true. And if it is true, then it will output the tag false. And if it is not, then it will try the next one. And and then it will output true over there. Okay, let's take another example. I told you that if I use only symbols, then Haskell interprets as an operator. So what about the and? There's a reason why I'm using a double ampersand over here to denote and. So what is true and true? Well, it's true. So I just write that there. I just say true and true is equal to true. So when you take X and Y, it will try and match X and Y with this pattern. And if it matches, it will output true. That means if X is true and Y is true, it will output true. On the other hand, if it does not match this pattern at all, if X, this is a convenient syntax that Haskell gives you. I could have actually used a variable X and Y, but Haskell allows you to use this underscore, which means that you don't care what it is, right? You don't care about what it is. So you know that and is an operator that will give you true only if X and Y are both true. So if it finds that the one on the left is not true, or if the one on the right is not true, in either circumstance, it will just be false. See how easy it is to define the and operator. I'm going to define the or operator in a slightly different way. As usual, if both are false, I would like it to be false. But this time, I'm going to just to illustrate something. I could have defined it to be, or if it's something else, define it to be true. Okay, but I'm going to define it this way. I'm going to say that if the left-hand side is true and the one on the right of the or operator is, then we don't care about it, what it is, and then you always output true. And then I'm going to say that X or Y is equal to Y or X. Now that's interesting, right? Look at the way I'm defining it. You would think normally that this will go into an infinite loop. XY is equal to YX. What is YX equal to? YX is equal to XY, and XY is equal to YX. Well, in fact, worse, you'd think that it will blow up the stack. But that's not how it works in Haskell because of the evaluation strategy. XY is replaced by the expression YX. So supposing you feed it false or true, then what it will do is it will first try to match false or true with false or false, and it will find it doesn't match. Then it will try to match it with true or whatever, and whatever. It will just try to see whether the first argument is true. It doesn't match. So it will come to this one. And this one tells it to flip the arguments around. So false or true is equal to, therefore, true or false. Now it'll try to evaluate true or false. It'll try to see whether it matches the first one. Doesn't match. Does it match the second one? It does match. So the output is true. That's how it will work. All right. So you can do these nice little things like this, make it more. In this case, it was unnecessary, but in some cases, you might want to emphasize that the operator is actually commutative, that it commutes. And if you can, the order does not matter. And so you can put this as a last pattern match. Now we are ready to define an if then else. Okay. Now, what do? I define, so if then else is the following. So the condition will come as the first argument. If the evaluates to true, then it should output whatever, it should evaluate and output whatever comes in the second argument. And if it's false, then it should evaluate and output whatever comes in the third argument. How do I define if then else? Well, if it's true, then I don't care what the second argument is, so I use an underscore. And it's simply this, right? If it's true, then simply output the second argument. And if it's false, then simply output, and outputting means you will also have to evaluate the second argument. All right? Now, in a strict language, this would be, you would not be able to do this. Why? What do you want from an if then else? If something is true, you wanted to evaluate the then thing and then output it. And if something is false, you wanted to evaluate the else part and then do it. But if it is a then you don't want to even evaluate the else part. In a strict language, what would happen is that even before it applies if then else, it will evaluate true and false. So it's doing unnecessary work over here. All right, and a lot of unnecessary work actually, if the then part and the else part are very computationally heavy. And so because of this choice of laziness over here, lazy by default rather, you can turn it off in parts. Haskell allows you to define your own branching operators or functions, and you can do it. And otherwise, in a strict language, you would have to wait for it to either be incorporated, or you'll have to use if then else, and things like that. All right, and your code you can't abstract things away and make your code more readable. All right, let's do something more complicated. Let's define natural numbers. Okay, this is not the way numbers are defined in Haskell. They're defined in a far more, they define using the actual number, the actual ones that are available in the machine. But anyway, let's just to illustrate the expressiveness of this approach of defining data. So I can define a natural number to be the following. It is either the number 1, or if I have a natural number, I do have a successor of it. So you can see that this is the way this is how I'm defining it. Okay. So for instance, what is the number 1? This is not, I'm not allowed to do this in actual Haskell, by the way. 1 is equal to this because 1, 2, and 3 and so on are already defined. So I can't redefine them. Okay. But I'm abusing the actual notation over here, and just to illustrate what is happening. So 1 is equal to this, and I could say 2 is a successor 1, 3 is a successor of a successor 1, and so on. Okay, notice that I could have said 3 is a successor of 2, but that evaluates to successor 1. And as I said, in Haskell, it's pretty honest. What's on the left hand side can be replaced by whatever's on the right hand side of the equal to sign. Okay, so when you say that when you're talking about natural numbers, for instance, you can see that you're either taking this just a single tag 1, or you're taking a natural number and you're defining a new thing called the successor of it. Notice that this is another instance of where there's a sort of recursion going on, or self-reference, right? I mean, on the right-hand side, I'm defining nat by using nat in its definition. Okay. Once again, it makes things more expressive, right? And that's what I would like. It's simply saying that a natural number is either 1 or it is a successor of another natural number. Therefore, since 2 is a successor of another, since you can have it is either 1 or a successor of another natural number, that other natural number could be 1, and so therefore successor 1 is 2. Now that you have 2 over there, you can also define 3, because 3 is a successor of another natural number, namely 2, which you just built. And this way you can build your natural numbers. Okay, now supposing you want to define a function, how can you use this, right? Maybe you want to define an iterate function. That is that you take a function f, and it takes an integer, let's say, and outputs another integer, let's say square, right? And you want to iterate that function. That means you want to apply that, say, a certain number of times, natural number times. Okay. So how will you define such a function? Once again, we're using pattern matching. If you apply it only once, so once again, let's use this logic that we've used before, which is try to see if I knew how to do it with something slightly simpler, then how would I do it? And then let Haskell take over and apply recursion. Okay. And of course, so this is an inductive way of doing it. And of course, you would induction means that you have to start with a starting point. And so in this case, if you apply the function only once, then of course you just want to apply the function. So you just take iterate of 1 fx is simply f applied once. What about iterate of 2? What is 2? Or not just 2, but any number. What do? I would say that, look, if I want to apply iterate to any other number, since it is not the number 1, it will be successor of something. Let's call that something n. N is simpler, right? So what I'll do is I will first, in fact, I could have done it in 2 ways. I can first apply iterate of n f and apply it to x, and whatever answer I get, I can apply f to that. Here I seem to have done the opposite. I seem to have applied iterate n f onto f applied to x. All right. Anyway, you know what I'm talking about. I'm simply saying iterate of a successor of n. If I knew what iterate does with the simpler n, iterate n of fx does, then I also know what the successor, what I should do to the successor. Namely, I should then apply f once more. Okay, so this is how I can define the iterate function. Okay, now so this is interesting, right? I mean, from just by using this what's called algebraic data types, which allow me to define these tags and which allow this sort of recursive definition, etc. It's very clean, right? And yet using this, I can define fairly complicated data types. Well, Boolean did not seem complicated, but natural numbers are complicated, right? Now, I can also do something like this. I can say, let me define a pair of a Boolean and natural number. How do I define that? Just this syntax. The way you should read this as is that a Boolean nat pair happens to be anything of the form B and P, and then the first argument should be a Boolean, and the second argument should be a nat. Okay? I can generalize this. You remember what we did in functions? What did we do? We took something concrete and we replaced it by a variable and we wrote it on the left-hand side. Okay, that's exactly what we're doing over here. I want to generalize this. So instead of bool, I write A and I bring an A on the left. So instead of bool nat pair, I'm going to call it a pair, a general pair. All right. And instead of nat over here, B. And so in order to refer to it, I have pair AB on the left-hand side. And so what is happening here is that my bool nat pair is therefore pair bool nat. A is bool and B is nat. Okay, natural numbers. And using this, I can define things like this. The pair of true 5 is an element of this, right? Because true happens to be an A, and since true is a Boolean, therefore this A is also Boolean, and 5 happens to be a B. Since B belongs to natural numbers, therefore this B is also natural numbers. So true, 5 belongs to pair bool nat. 7, 5 belongs to pair nat nat. Okay. Once again, notice how light the syntax is, all right, and notice how expressive it is. Okay, all we're doing is we're saying that I'm defining a new collection of data. I'm defining a more complex data type. I'm combining Boolean and natural into one unit, and I'm calling that unit a pair, right? And in fact, I can choose whatever tags I want over here. All right. Now, Haskell defines its own pairs. It's more, forget this. This is a typo. This at the rate of symbol over here. But Haskell defines a more convenient syntax, and which is just a tuple, just like you've seen in Haskell. So in Python. So for instance, you could have true, 5 or 7, 5 put in parentheses. Okay, so that's a much more convenient syntax in this case. Otherwise, when you're defining a data type, you must define it this way. That is, it's always in prefix notation. Actually, you can use infix notation if you use symbols. Okay, but the parenthesis is what well, actually, no, the comma is used. Anyway, let me not get into that and confuse the issue. It's not important. Okay, now think of it as just some convenient syntax that Haskell provides. Okay, let's go to the next level of complexity. Let's try to define what a character is. Well, a character is simply, A, B, C, or whatever. I put them in codes like this to separate them so that, one does not confuse it with something else. Oh, another thing that I forgot to tell you, you might have noticed that all my data types are defined, even the data types as well as what I call data constructors. They're all defined with starting with an uppercase. And this is a convention for, not just a convention, it's enforced in Haskell. Haskell expects those which start with an uppercase to deal with data, and those with lowercase to be functions, okay, or values, okay. So, but functions are values, and values can be called functions with no arguments. All right. So, in fact, by the way, one more comment I would like. What does BNP do, or what does PR do over here, or what does suck do over there? What they do is they are taking some argument. So when you apply PR true 5, what is it doing? It's PR is something that takes a Boolean as a first argument. It's actually a function. It is a function, but a special kind of a function, which doesn't do anything else other than creating a new data type. That's all. It just does nothing else. So PR is a function of 2 arguments, and you know how to reduce that to a function of 1 argument. But it's a function of which takes 2 arguments. One is a Boolean, one is an integer, and it gives you a pair of bool nat. Let's look at suck. What does suck do? Suck takes it's again a function which takes as an argument an element of nat, and it outputs another element of nat. It gives me a new element of nat. All right. So they are functions, but they're functions that don't do anything else other than creating a new. They're what are called data constructors. They either construct more complicated versions of your same data, or they construct or they combine data into more complicated ones, into compound data types, as you would like to call them. Okay. All right. So we define what a character is. It's just simply, all of these tags. You probably want to include numbers also. What is a string? A string is either empty, or it's a combination of again, ask yourself, how can you make it one step simpler? So if you take a string and you take away the leading character, what do you get? You get a simpler string and the leading character. So a string is simply either an empty string, or it's a combination of a character and implicitly, it's implied that it's a simpler string. Okay, that's what a string is. So how do I represent the string no, for instance? Well, I would represent it as a combination of n with a simpler one, which itself is a combination of O and the empty string. I need to end with the empty string, otherwise it'll go on and on. And in fact, in Haskell, you don't need to use this unwieldy notation. And Haskell has the string data type, and in fact, it gives you the syntactic sugar like this. All right. Now, let's try to generalize this whole idea of a string to what is called a list. Yeah, go ahead.
The time.
Oh, I see. I'm so sorry. Yeah, I don't have this thing. So, oh God, I seem to have exceeded my great deal. My goodness. All right. It's how much more time can I actually take, really?
There isn't any such limit as such, but
yes, I know. But if you could just impose one on me, otherwise I'll.
I think if you could finish by 6:55,
all right,
then another 5 minutes of questions, and then it'll be a 2-hour.
Yeah, all right. I'm so sorry about this. I think I completely blew it in the beginning by going into all those tangents. Actually, I was worried about this, but at the same time, I didn't want to cut down. There were so many interesting things, and I didn't know which ones to leave out, actually. Anyway, I hope it's not tiring already. I hope you're able to follow. I mean, I don't know. Maybe I know it's not a lecture, so all of you I can't really know your response. But in case somebody, in case it's turning out to be hard to follow, I'd appreciate it if some of you at least respond and let me know, because then it defeats the purpose anyway. Okay, and then I might as well just wrap up quickly. Okay. All right. What I'll do is I'll now, since I have less time, I'll try and keep it a bit lighter, and I'll just tell you what things are without going into much of details anyway. All right. I'll just zoom through and just tell you, look, this is what is interesting about it. Okay. So in Haskell, you can generalize your like we had you can generalize things, and you can make sure that you can have what's called parametric polymorphism. So you can in one stroke define a list and not have to define list of strings separately, list of integers separately, list of booleans separately. What you do is you simply use a variable, and the syntax is just as before. You simply replace the string that we had earlier with a more general form of list A. So you see, we're going to ultimately write a string as list char, and we want to generalize character to any A, right? So a string is a list of characters. We haven't yet defined list, but we're going to define list in this manner, okay? And so here you can read this as it's either an empty list or it's a combination of A. A list of A's is either an empty list or it's a combination of A with a simpler list of A's, all right? And once again, Haskell has convenient syntax for this, for all of these things. When you want to combine an element with the list that is already defined, you simply you can use this colon notation. And if you want to instead of list A, Haskell uses this to represent the type. It uses a notation box bracket A. So box bracket string would be a list of strings. All right, that denotes the type. Empty list is denoted by an empty box. And a list of 1, 2 is simply syntactic sugar for 1 combined with 2 combined with empty. All right. So 1 is combined with a list, which itself is 2 combined with the empty list. All right. And by the way, this might seem a little confusing, but they belong to separate namespaces. The same notation is used for the data type as well as for the actual data. All right. But Haskell allows that. All right. I won't go into it now since I've spent an awful amount of time on just rambling away. But you can also define trees very easily. I will not tell you how, but it's very similar to tree. All I wanted to observe is how it's just one line. That's it. And you can define binary trees. You can generalize binary trees, and you can define rows trees, what are called rows trees, where where instead of just 2 possible branches, you have a list of branches. Then you can do something even more interesting. You can even generalize this list. List is special. You see, list A is a type, but list is something that takes another type, right? So you have to, it's like dangling, right? You have to have either a list of string or list of char or list of bool or list of int. But if you have only list, what it does is it takes a data type, it takes a type, and gives you the list version of that type. All right, so it takes a type and gives you another type. So it's a sort of a function on types itself. All right. And what you could do is in Haskell, we can ask, look, in abstraction, what do? We just take a small part of it, we give it a general variable, and then we just put the variable on the left-hand side. Can you do it even for list? Rather than list A, can you do it just for list alone? And the answer is, why not? And Haskell allows that. And so what you can do is you can generalize this particular tree so that these rows trees, so that not only are the branches a list of elements, you can even have it as a function of elements and so on. Okay. And so on. Okay. Even if that's confusing, the point is that there's a lot of abstraction which is possible in Haskell. All right. Let me give you some examples of interesting data types. There's a data type called maybe A. What does that mean? What is this data type used for? It's used to represent values which may or may not exist. Okay. So for instance, let me ask you, supposing you look at a function which you want to apply what are called partial functions. Okay. Let's take square root. All right. And ignoring complex numbers and things like that, it does not make sense to take the square root of negative integers, let's say, or negative float or negative double, whatever. So ignoring complex numbers, let's say that the function outputs just a real number, and since it does not make sense, one way that it would do it is to just give output an exception or something of that sort, or just terminate the program or whatever. But in that case, things are not are not being taken care of by the type, and I'll come to that a little later, what that means. But just think of it this way: that if when you're taking square root, if it's possible to get a square root, then you would get just an integer. So in that case, you would get, let's say I'm taking the square root of 4, it will output just 2. And if on the other hand, it's a negative thing, it will just output nothing. Okay, so just and nothing are just special tags which are used by convention, and which is a data type defined. You could have defined it yourself, but Haskell has already done it in one of the libraries. And so what it allows you to do is to, in values where it allows you to honestly describe. So essentially, when I say maybe integer, what I'm trying to say is that this value may be an integer, but it may not be an integer, or it may be nothing. Okay. And it's useful when the output, when for certain inputs, these are called partial functions, for certain inputs of the data type, you output nothing. Ideally, you would like to output nothing, but this being a computer, you have to output something. So instead of outputting garbage, you be honest about it and you say, look, it is not outputting an integer. It is the output is actually maybe an integer. And if in case it is that, then it will give you just 5 or whatever the value is. But in case it isn't, it will give you nothing. Okay, and similarly, you can define what is called an either data type. It allows you to combine two things where it's sort of like they're taking the union. And you can see there's nothing special about the definition. You could have defined union of 5, 6, whatever you want, any number of data types. You can combine them in this manner by taking effectively what's called the disjoint union. So here, what you're trying to say is that the output of this particular function, or even the input for that matter, if it is either A, B, either int, bool, so which means that either it would turn out to be an int or it would turn out to be a bool. Now, in an unprincipled language, it might just say, well, you can just, who cares? Well, it's all one part of the same data type. But then you're not tracking things very well. It's not being very honest, okay? And it can be confusing and hard to, follow and reason about the program. So instead, the data type is that it will not output an int. No, it's not outputting a bool. It's outputting either an int or a bool. And if you see it tagged with the left, it's an int. If you see it tagged with the right, it's a bool. However you choose it. And you can use pattern matching to decide what to do if the output is an int, what to do if the output is a bool, and so on. So you can think of this as allowing you certain unions and so on. And you can use this for even, outputting errors and things like that. Now, I don't need this very well much, so I'm not going to bother about this. Okay. Now let's come to, I told you about C being a statically typed language. Haskell is also statically typed. Okay. Now that seems one step backward when you're familiar with things like Python and so on, which are dynamically typing. You don't need to mention the types. You don't need to mention the type. Actually, in Haskell too, you don't need to mention the type strictly. Okay. Although the types are taken care of during compile time, you don't need to actually mention the types in most cases in Haskell. Okay, because Haskell has what is called a type, it's called a Hindley type deduction system, which basically can deduce the types. There's a particular method which was developed, and it's not just Haskell, even ML and OCaml have these kind of things. In fact, because OCaml and ML have not made certain choices that Haskell is, I think it works in a less complicated way there, and therefore there it's even more true that you don't have to, in most cases, you don't have to mention the type. In Haskell too, you don't have to mention it in most cases, but in some cases, it cannot deduce the type, and so in that case, you have to help it a little bit, but you don't have to annotate each and everything. You don't have to tell, supposing I'm saying x equal to 5, I don't have to always say, oh, 5 is an integer. All right, it can deduce that. And anyway, so that's one advantage. But what is the advantage of a statically typed language over dynamically typed language? It's a huge advantage. What happens is that if you make a type error in a dynamically typed language, you may not detect it, because you only detect an error if the input is such that it requires that particular branch of the computation that where the error is. Okay, and so it depends on the kind of test you do. You can mitigate it and you can increase the probability that you've detected all these errors, but there's no way of proving that, rigorously proving that there is no such error, because more often than not, the amount of inputs that the program can potentially take are infinite, and you rarely have and you can't test for all of them. Okay, but if you make a type error in a statically typed language, which checks that if you're applying a function on so and so thing, it will check whether the input of the type of the function matches what you're applying it to, and so on, and checks all these kind of things. Then, if it finds that there is a mistake, it will reveal that to you while compiling. And if you're annoyed by that, if you're annoyed by all these compiling things, you're basically saying that you just want to live in fool's paradise, and that you don't that you'd rather that it was not revealed to you, and that it is lurking somewhere there, waiting for us to give you a nasty shock when you're for certain inputs. Okay, so that is the advantage of statically typed languages. Again, the price for that is that the compiler should know the types, and in languages which don't have this type reduction system, there it's a pain in the neck to actually go and mention the type for each one. But as I said, in Haskell, you don't necessarily need to do that. However, this is another very interesting feature about Haskell, and I hope I have the time to actually give you some feel for that. Because this is something that the compiler can do, it becomes a very very simple but can be made effective way of checking for errors during compile time itself. And as a result, the way people write programs changes. Let me give you an example. If, let's say, you are trying to represent the name of a person, okay, or let's take something else. Let's take a phone number. If you're trying to represent a phone number, your first instinct will be, oh well, I can represent an integer. In Haskell, if you get used to this kind of thing, you will never do that. You will instead create a new type, which is effectively a clone of an integer, but which is nevertheless, to the type checker, a different thing than an integer. Why would you do that? Because supposing accidentally you forgot that this particular name denoted actually a phone number, and you thought it denoted some other integer, and you tried to add them together. I know I'm giving a very contrived example, but believe me, these, I mean, I can't tell you how much you can exploit this particular thing without giving this example. More complicated examples would take much more time. But the point is that if you're trying to combine two phone numbers together, it doesn't make sense. You can't add two phone numbers the way you're adding integers. Right? So you don't want to permit that operation. And the compiler will warn you that when you're doing this, the compiler will say, no, what you're doing is complete nonsense. These are phone numbers. And you nowhere in your program have you defined what it means to add two phone numbers. Okay. So, and I'll come to the other advantages of this. Anyway, this is what, so in this case, X is 5 and 5 is an integer. So this is the syntax you use. For functions, you use the following syntax. You say, this is a function that takes an integer, outputs an integer. So the syntax is input type, arrow, output type. All right. What do you do if it's a function of many variables? If it's a function of many variables, then, as I said, what happens? It's a function that takes an integer and outputs a function that takes an integer and outputs another function, right? So you would write it this way. But Haskell recognizes that this parentheses might be a little unwieldy, so the parentheses is implied, and it allows you this much cleaner syntax. So whenever you see a syntax like this, several arrows, what it means is that all except the last type are the input types. This is the input of the first argument, the second argument, and this is the last one is the output. Okay, so that's how you should read it. So any type separated by arrows means it's a function, and there are lots of them. That means there are lots of arguments, and the last one is the output type of the the type of the output of the value. All right, now I come to something very interesting. It's called parametric polymorphism. As I said, you can define. You see, in C, you have to, if you want to define a function, you have to define it on either either an integer or a string or whatever. If you're defining a function on an array of some things, well, you have to define a different one for array of integers, array of strings, and so on. If you, let's say, want to see the first element and so on, or something more complicated, okay? But in Haskell, it allows you to abstract over these kind of things. And this is what's called parametric polymorphism. Instead of the data type, you can actually keep a variable. These are called type variables. These are variables on the level of the type, not on the level of the value, okay? So let's look at an identity function. I can define an identity function for any type. What does it do? It simply takes the value and does nothing to it. So how would I define identity of an integer? Identity of 5 is equal to 5. Identity of x is equal to x. In fact, identity x is equal to x is exactly the way I would define identity function for integer, for string, for any data type for that matter. Okay? So in fact, identity is a function that I can define from any, it is a function which can have the following type signature. it takes as input any data type you want, and it outputs a value of exactly the same data type. Now, here's something very, very interesting, which helps you to use the compiler to detect bugs at the level of compilation rather than waiting for runtime. How many functions can you think of which will have this particular type? That means it takes as a value of a type A, where A can be anything at all, no constraint whatsoever, and it outputs a value of exactly that same type, right? So that means it's not something of type signature A going to B, it's something of type signature A going to A. How many such functions can you think of? Remember, this function that you're defining has to be general, because the signature of the function is general. You are not saying that this function on int, it's from int to int or string to string. You're saying this function works no matter what the input is, whether it's an input, whether it's a string, whether it's an integer, or whatever it is, right? What can this function be? What can this function do to x? So that, supposing for instance, try to square it. Well, then you're assuming that the input is a number. You're assuming that A is a number. You can't square a string. You can't square. There are some languages that allow you to do nonsense with anything, but in Haskell is very principled in that sense. It will not allow you to just square. It won't allow you to do something that does not make sense, right? So you can't square a string. You can't square a list of strings. You can't square anything you want. So it can't be a square. It can't be many of the other functions that you could think of. Actually, it can't be anything else other than identity. And this is a very important observation, that if you choose your type signature to be general enough so that the function, you've chosen your function so that it applies on a wide variety of types. So then there are very few functions that can actually fit that particular type signature. And therefore, if you have made a mistake, it's very unlikely that your mistake is so unfortunate that you actually got one of the other rare functions with the same type signature, and therefore therefore the compiler will most likely detect it at the compiling stage that you've made an error, because there will be a type error, a mismatch in the type. Okay, you see, so it helps to do that, and this is I found this to be a very revealing thing when I first came across this thing. Look at the constant function, for instance. What does it do? It ignores the second argument and simply outputs whatever the first argument is, right? So so this is what constant C does. Again, there's not much of a choice, because it works for any A and B. A could be int, B could be string. It works for any A and B. All right. So you can do all sorts of functions like this, and this changes the way you actually program, the way you think about programs. Now, even if you can do something, even if you want a function for integer to integer, you try and express it as a composition of more general functions. You try and express the function as a composition of simpler functions, combination of simpler functions, and each of those simpler functions, you try to make them as general as possible, even if you're using them for something very specific. Why? Because if you have a very general type signature, what would happen is there are very few functions which would satisfy that particular type signature, and therefore, if you have made an error, if you've made some mistake, it's very unlikely you've made your function and in fact, some cases there's only one. So if you made any error, it will show up during compile time. Your function will just not compile. Forget about actually compiling and running. It will just not compile. Okay. And there's another advantage. Let me show you this. This is a very interesting thing in Haskell. It's called Google. Okay. And what it allows you to do is it's like a Google for Haskell, which allows you to search for things. So let's say that I want a function which takes, and never mind if you don't understand the basics, just observe what I'm doing. I want a function which I'll get as output a list of B's. So what am I doing? I've got a list of A's, okay, and I use that as well as another function which simply takes an A to a B, and I simply and I want to get an output of B's, and I want this to work not just for integers, not just for characters, but no matter what A and B are. Well, you see what the top thing is? Map, 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 fmap. Fmap is a kind of map. All of these are maps, 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 because there are very few functions that can actually have this particular type signature. You see? And so this is another way you can actually reason about Haskell code and the way you can actually work out Haskell. You try to compose your functions in these very general type signatures, and then you go onto Google and you type in the type signature. And if you're lucky, someone may have already done something like this for you. Someone may have already combined something like this. Let's look at another example. Supposing I want to take a list of A's, right? And I want a function that will take something that takes a binary way. It takes a way of combining two A's and outputs an A. And what I want is, I want to take a list of A's and I want to combine all of them. So what would I do? I would want to use, I want to take a, so supposing I take a list of ints, right? And I want a function which will take the plus operator acts on only two, and it also takes a list of integers and it applies the operator plus several times so that it crushes that int into one single integer. So what is the type signature? A to A is one of the inputs. That's why I parenthesized it. It's one of the function inputs. And I've also given it a list of A's and it should output an A. Well, what do you think it gives me? Fold, 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 fold. Because that's exactly what I'm looking for. Fold, in fact, is a function that when you, which will take an operator and it will take a list and it will use that operator to combine the list into one single element. Right? So isn't that wonderful? I mean, now you started reasoning, you're using the types, which was earlier, which if you're used to C and you come to Python, you think of the type as an annoyance. But now the type is actually something you use to reason about your code. And in fact, it's, although Haskell does not require you to put the types, many people actually put the types. I myself program always putting the types. And in fact, you have things like, your Emacs has a feature which will allow you to extract the type. It uses some other tools to do so, but it extract the type of the function and it'll put it on top and so on. And, sometimes you just want to put the type in. And in fact, reading Haskell documentation, you don't even have to read the words. Sometimes you just read the documentation and you just look at the types, and just that gives you so much of information about what the program is going to do that it's very quick to read it once you get used to all of this. Okay, so well, these are some more examples, and I won't go through all of them. Okay, so I'll skip through all of these things. How much time do I have now? I think
sir, it's 7.
Oh God! All right. I'll stop here. Okay, I'll just end with one small little observation, and then I'll stop. All right. Supposing you, how do you deal with state changes in Haskell when you really need it? All right. Now I won't go through the details. I'll just quickly tell you that whenever you want state, it is actually possible. There's actually a hidden operator. See, in other languages, you do something like x is equal to x plus 2. And then some few statements later, you say x is equal to x squared or something of that sort, right? So you're changing the state. Now you think, well, in Haskell, if you try just writing one thing over below another, it won't make sense, because in Haskell, there's no such sense at all. Functions take as input and they give you an output. You can't just chain functions one below the other. So what you do, however, there's a hidden operator over here. You know that semicolon that you see in ordinary languages? That's actually a hidden operator that allows you to take, and you can define that hidden operator in Haskell. Okay. Anyway, I'll cut a long story short and just tell you this, that you can define this particular thing in such a manner that you get syntax which is almost like what you're familiar in your imperative languages, where you write statements. And Haskell provides this thing called the do notation, which is just syntactic sugar. And that's very important to realize, because even if Haskell did not provide that notation, you could have written a preprocessor to actually get this notation over there, which would convert this into something like this. It's quite easy to actually write a preprocessor, but Haskell does it for you already. And what happens is that when you need it, then your Haskell code, when you're actually using state, then you have small parts of your code looking like the code of imperative languages. But normally your code looks like far closer to the way we think rather than the way the machine works. And so that's a brilliant thing. And there's also this thing called monads, which you should check about, but be very careful, because there are lots of tutorials which are not very accurate in monads. You can ask me later if you want to know good references for that. But they generalize this whole idea of states and so on. And this is another thing which I found very, very amazing in Haskell. It's not just Haskell. I mean, many languages can actually incorporate this, but Haskell is the one that invented it out of necessity. And which is that when you think about, if I ask you the following thing, what is common between change of state and functions that output possible values? Rather than outputting one value, they output possible values, and functions with the possibility of failure. That means they can output some value or they can output nothing. What is common? And also one more thing, functions that output probability distributions. What is common between all of them? Well, you would say nothing. Well, they're completely different things. But this is the cool thing about it, that if you actually look very carefully you see what is abstraction? You look at your code and you see a certain pattern matches with a certain pattern over here, then you can abstract it out, right? Well, it so happens that in all these three things, there's a lot that you can write that and reduce them to two functions, okay? And those two functions are what are usually denoted by this symbol and return, okay? Why are they denoted by the same thing? Because that is what is common between them. They follow, they are functions which have the same type signature, and you can characterize them by what are certain called monad laws. I know I'm not making sense over here, but I just want to tell you this, that this thing is an abstraction which is so general that and yet so expressive that just by knowing what the interpretation is. So the same thing, if let me put it this way, if f and g were random values, this would return a random x squared and a y. If f and g were functions, were actually lists, it would return all the possible combinations of the square of this list and the other one. Okay, and if f and g were probability distributions, it would output all the possible combinations with their respective probabilities. And if f and g were possibilities of failures, it would only return something if both succeeded. You see, what is happening is that several things, I have a common way of thinking about them. And the best part is that I can actually use my intuition to predict what these common functions will do in each circumstance, rather than going into the actual implementation of it. And therefore, it's much easier to reason about. And therefore, another habit that we have in Haskell is that every time we define a particular new data type, we always ask this question: is it a monad? Can we give it a structure of a monad? Can we give it a structure of this, etc., etc.? Okay. Once again, it may not make complete sense to you, but it's time is our biggest enemy here, and I can't do justice to it, but I hope that I've got you interested in it so that you can look it up elsewhere. All right, sorry. I'm really sorry for exceeding the time so much. I didn't have a clock in front of me, and there was a lot to say. Yeah, go ahead. What are your questions?
Yeah, so we've, as of now, there have been 2 or 3 questions.
Yeah.
I think when you were talking about the, what is that? The infinite series part of the thing, there was a question which said, is that symbolic programming?
It is. It is symbolic. So the point is that Haskell, so here's the thing. It's symbolic programming that you can implement yourself very fast. Okay, it's hardly a few lines. Let me show you the thing. This is literally doing the symbolic programming for you. So using your ordinary data types, I've already given you all the tools to actually do this symbolic programming. So it is implementing a symbolic programming, as a matter of fact, but it's doing it pretty fast, actually. I mean, quite easily. So yes, when you normally think about symbolic programming, you think, well, it's something that will require a lot of thought and things like that. Well, because of certain choices, in this case, it does not require that. I must say, however, that there hasn't been too much of interest in Haskell among Haskellers, because it's a smaller community than Python, to make a counterpart of Python's SymPy or something of that sort. Okay, so yeah.
Yeah. So the next question is, when we use recursions,
yes,
would there be a overhead?
No. Well,
I think the question was asked as a comparison with for loops in both functional programs and other types.
See, functional programs, since they require, I don't know the exact answer to this question because I haven't compared the two, but since functional programs, recursion is the bread and butter of it, I imagine that these things would be heavily optimized by the compilers. And the compiler designers would spend a lot of time making sure that there is, everything has an overhead, but they would try to make sure that there's very, very little overhead. Oh, you must also realize one thing, that in fact, I know, see, Haskell, when it compiles into a lower level thing and so on. And I think at times, although you never have to, it's never exposed to you, but at times Haskell may feel that, look, this particular recursion, the compiler may realize that this particular recursion actually can give you, can be at a low level thing which is hidden from you, be converted into a loop. So it might do that. Okay, and this is one more thing about being referentially transparent, that Haskell allows the compiler to do a lot of rearranging of your code with the confidence that it's not breaking your logic in your program. It's not affecting it. It's only modifying the performance. It's not destroying the correctness of your program. Okay, so
right.
Well, yeah, because it's
So the next question was that when we've defined types and data types or data, you can very easily explain what you basically did was you used a CFG, a context-free grammar.
I'm sorry, I used that a context-free grammar. Well, no, it is like a context-free grammar. Yes, indeed, it is.
But what about data types which can't be represented as a context-free grammar, like real numbers? How would you
real numbers? You can see. How can you represent a real number on a machine? Right, you can't.
Right.
So I'll give you an interesting. So first and foremost, real number on a machine is of course impossible, right? Because even if you want to exhaust all of them, see, I could. All the integers I cannot see. Haskell uses laziness, and as a result, you can, as you go from one integer to another, you can get more and more integers, but you can't exhaust them, right? You can't take. Theoretically, you can. That is, given any integer, however large, you can ultimately reach there, right? Because integers are countable. So rational numbers I can represent. How do I represent them? Well, I'll just take, I call it rational a comma b, where a is also an integer and b is also an integer. So I'll interpret the first one as a numerator, and the second argument as a denominator. So rational numbers, I can do that. But but if I wanted to represent real numbers, I have to represent it in a machine. You see, there are real numbers that take an infinite amount of information, right? So you can't really, even that single real number, you can't represent it in a machine. So what I could do is I could do it in the usual way that, like a float or a double or whatever. So I could represent it as a string of zeros and ones, maybe. That could be one way of doing it, all right? Represent it as a string of zeros and ones or something. So it's an approximation to that, okay? So that's the only way out. It's not the only way out. You cannot represent all the real numbers faithfully on a machine. Okay, that's impossible anyway. But what you could do is, you remember the power series that I told you about? So you could represent real numbers by infinite sequences. Okay, you'd have to check whether they're convergent or not, or by infinite series. And so that you could possibly do, and quite a lot of real numbers you wouldn't get a handle on. Okay, but real numbers where you can actually define the coefficients recursively or something of that sort, you can do that for your pi, because pi is 1 plus whatever that series is and so on. You can do that for pi. You see the coefficients, the pattern. It's infinite amount of information, no doubt. But each of those infinite things depend on a function like this. So yes, you can do that. You see. In mathematics, you represent a real number as a sequence or as convergent sequences or a series and so on. So that you can replicate over here in Haskell. You can do that.
Right. So there was another question which was, I think Akshay asked. Akshay, do you want to ask it yourself? Okay. So the question was, why isn't Haskell famous even within the scientific community?
Yeah. Okay. So I think I was telling you. So first and foremost, Haskell has a reputation, undeserved, I feel, for being very difficult to comprehend. In fact, the inventor of Perl, Larry Wall, said that it's a language by geniuses for geniuses. I may agree with the first part. I don't know, but I don't agree with the second part at all. So what I feel is that Haskell, because it at one shot, it has so many concepts. Yes, it takes time to get used to them. That is true. And the other thing is that for most people, Haskell is not the first programming language. So they have some context elsewhere, and then they come to Haskell, and then they bring all that baggage and they expect things to be in a certain way, and that kind of weighs them down. Apart from that, Haskell itself has made some choices. You see, I like to see it this way, that all these languages have a certain center of gravity, right? They say that, look, this is my main core thing that I'm going to focus on. In addition to whatever extent, I'm going to try to focus on other things. Haskell's center of gravity has not been practicality. In fact, Haskell, when it started off, was far less practical than what it is right now. Okay, Haskell said that, look, referential transparency is a good thing. How did Haskell develop? At that time, when Haskell was being developed, there were a lot of lazy functional languages which were being experimented with and so on. So Haskell was like, let's take all the good points of them. Let's try to see what we learn from them. Let's come up with this language, so that there's one language that we can deal with rather than several of them. And so what Haskell tried to do, what Haskell did was, it said, look, we are going to remain pure. Most other languages, even though they may have started with that particular thing, have ultimately given up, because it's hard to be pure and be practical. But what Haskell did was, it insisted on it. And as time went by, people innovated. People invented ways of circumventing difficulties. And now it's come to a stage where it is quite practical. But since its root is still there, it still follows this. Its motto is avoid success at all costs. So Haskell the compiler goes through a lot of changes. People are experimenting with the creators of the language, experiment with the language a lot. So their priority is not that it becomes like the language that everybody uses, because then there'll be backward compatibility issues, and then they will not be able to experiment much with it, right? So nevertheless, it is used in practice in certain places, but because one major reason people cite is because there are very few Haskell programmers. There are very, very few Haskell programs. There are very few people who actually know and understand and appreciate Haskell, which is why there are few tools in the first place which are developed. The scientific community also has to learn this new language, and it is undoubtedly more harder to learn than Python, for instance. Okay, and so that's the problem. And but by the way, Facebook's spam filtering apparently is using Haskell now, and so on. So there are pockets where these are used, and I think even in one of those big finance companies or something, I forget now which one, but they also use Haskell. So yeah.
So I mean, another thing that I've generally seen is that the scientific community does not care much for new languages, because for them the language is a tool.
Just a tool.
And let's say once I've learned the C++ or Fortran or whatever, then I don't. It's a tool that works, and then a lot of people don't really want to change.
Exactly.
Even though there are.
Here, let's make a comment that Haskell tends to be appealing to people who are mathematically minded. When I say mathematically minded, I don't mean computationally. I mean abstract mathematics. Category theory and things like that. They use that in Haskell also. Although it may not be required for actually programming in it, but some of the underlying concepts are there. Haskell is some of the concepts are quite deep, right? So I can't really do justice to it. But I know that Professor Kapil Paranjpe also knows Haskell and has programmed in it, and he likes it. And I know of someone else who is also a hardcore pure mathematician, but also likes Haskell and uses it a lot.
Right. So I think there are no further questions, so I'll ask this. At the end of the day, because most of the computers, the hardware of it is basically a Turing machine.
Yes.
Well, it's a finite automaton because of finite memory, but theoretically it's a Turing machine.
Yes, right.
But the functional programming, if I have to simulate it, or let's say the lambda calculus, if I have to simulate on a Turing machine, while it is possible because of the equivalence, isn't it inefficient? And then, because at the end of the day, it is still a Turing machine.
Comparatively less efficient if, let me put it this way, you lose out on some opportunities of efficiency that you would have if you were just on a Turing machine, using a Turing machine as it is. But there are a few, so that is true. But as I said, you see, what has been found out is that Well, now that computers have become more and more powerful, and even before that, getting the last drop of efficiency turned out to be far less important than making sure that you could reason about programs much better. Okay, so it is believed to be a small price to pay for a lot of tasks. For some tasks, certainly not. I mean, if you're designing a game, if you're designing one of those, high graphics games, I don't think functional programming, a functional programming language would be a suitable tool for that job. In those cases, yes. In those cases, you would want something like C, where you have full control. But that is in principle. In practice, you might say that, well, I'm going to make something very perfect, but it might take you a hell of a lot of time. And not only that, things can get so complicated that you can introduce bugs that you may not even detect. Okay, so that is why there are so many functional languages. Haskell, by the way, in a lot of cases, because it's a compiled language. By the way, don't underestimate the speed of some of these functional languages. And this is one very important point. You see, what you're saying is correct if you're willing to do all the dirty work to have full control and do the best possible thing that you can to make it very efficient. Then what you're saying is correct. But in practice, that never happens. In practice, it's complicated. And in practice, there are some things that you want to be automated. In practice, you spend a lot of time and things like that. But one important thing that a purely functional programming gives you is that because the compiler knows more about your code, it can actually alter your code and make it far more efficient. And this I cannot, I cannot even stress this point enough. There are times when I have compiled something and then I turned on the optimizations. And it's fun to turn on the optimization to make it verbose. So you see all the optimizations that the compiler is kicking in. And you see a whole list of optimizations that are kicking in, and you see the dramatic speed up. Okay, dramatic speed up in that particular thing. I should not. I mean, you should be a little careful. I have been impressed by it, but of course, I'm not trying to say that it will be that you can't write a C program. Optimizations and things like that, and tries to do all of that. So you are protected from it. You are protected from it, and you don't have to bother about it. If you're, by the way, Haskell has this thing called the foreign function interface. What it does is it allows you to import C functions, interface C functions within Haskell itself. And the reason why it's given is supposing there's a part of your program which is extremely performance critical. In that case, but it's hopefully a small part of the program that writing it in C is not going to be a big headache.
I think he got dropped.
Yeah, that happens a lot in seminar course also.
Yeah.
Maybe
Let's wait. Yeah,
Yeah.
let's wait for another 5 minutes, and if he's not back, then we'll.
He's here.
Oh, he's here. Okay. Yeah, so you're still, you need to connect to the audio.
Yeah. Sorry, can you hear me?
Yeah. Yeah.
I seem to have lost connection on the laptop, but anyway, since I'm done with that, I can speak over here. So yeah, so about the performance, and in fact, there is this book I put up as a reference, which is called High Performance, Haskell High Performance Computing. You can check that, and it talks a lot about particularly how to get very high performance from Haskell. There's another language called ML, right, which I told you about. ML had a compiler called Milton, which is what is
called a whole program compiler. What it does is it takes even though you separated your program into many modules for organizing things much more in a sane way. It can perform a compilation which compiles all of them together, and so as a result, it can inline functions across modules, all sorts of things. It can do that, and and that also and that can also give you very high speed ups. So you see, the point is that when you restrict only to functional languages, optimization and better speed is one of the reasons why you would choose functional, because when you have referential transparency, it means that your functions can be rearranged, which gives the compiler more opportunities to optimize your code in manners that would be boring for a human being to do. Okay,
right.
So that's one thing to keep in mind. Yeah.
But for example, an area which is where mutation is imperative, for example, in image processing, where you have a large matrix or an array of numbers, and in a mutable language.
I'll just quickly give you a response.
Yeah, in a mutable language where, sorry, I'll go ahead.
I'll just tell you this. So Haskell does allow mutable variables, but the point is that the compiler, that the type checker tracks it. The type checker knows that this particular part of your code deals with mutable things. So Haskell does allow that. And in fact, if you were going to do something like that, you would be allowed to use mutable variables. But the way the Haskell language is designed, you would be doing it in a certain part of your program, which is clearly demarcated. And there's another clever mechanism that Haskell uses, which is that the mutable variable, it will demarcate in such a way. You can look at what's called the ST monad, and it will is the state thread monad, and it does it in such a way that the mutable part of it does not leak out. So you see, the dangers of mutability are confined to just that part, which is completely tracked by the compiler and you. All right.
Right. So, as a final question. Have there been hardware implementations of lambda calculus?
Yeah, I don't know. In fact, I think it's a good question, and one should, if at all, there's probably a candidate for Lisp actually. So I think I've heard of this thing called Lisp machines. I don't know whether the hardware was designed especially for that, but it's something that I wondered also, whether it's actually possible to just do that, and whether there was any attempt at it, and if not, then why not? But I don't know the answer to the question. But search for Lisp machines or search for this in Lisp would be a good candidate for it, I would say. Right.
Are there any other questions? Yeah, okay. I suppose there are no other questions. I think we can close the meeting. I thank you all for attending, and thank you, sir, for taking this long.
Yeah, thank you so much. Thank you. Yeah. Right. Sorry for the huge delay, but thank you.
So the meeting is ended. But sir, I just had this idea because it seems as if the functional programming isn't a topic that can, we've barely touched it, and still it's so large and it's so interesting. Is it possible? Is it possible if we can have, let's say, a mini course on functional programming where we don't really have where it's not actually institute sanctioned course?
Right. May I discuss this over email, please? My sons are actually getting a bit restless, and
sure.
I think
sure.
So I'll just tell you over email then. Yeah. Thank you so much. Okay. Sorry for the.
Yeah. That's it.
Okay. Bye.
Bye, sir.